Okay, so now we have Mark Nelson from University of Wollongong presenting Snap, Crackle, Pop models from the field of reaction engineering.
Thanks for the introduction. And good morning from the East Coast of Australia. So when we teach mathematical modeling, sometimes we want students to learn how to develop models from first principles. Even in the differential equations course, we might want students to learn how to develop models from first principles. But sometimes we want to give students models that already exist so that they can practice their mathematical skills, their analysis skills, and maybe even their report writing. So in this presentation, I'm going to talk about some simple models. And when I mean simple, I mean linear differential equations. So models that we can use in a first differential equations subject. And at the end, I want to talk about a much more complicated problem, which is, can we use mathematics to improve our breakfast cereal experience in the morning when we have our breakfast cereals? What is reaction engineering? It started off as a discipline of chemical engineering in the 1950s. And I've said chemical engineering using speech marks because, chemical engineering's evolved a lot since the 1950s. Food engineering, environmental engineering, process engineering, biochemical engineering, wastewater engineering, process engineering. These are all areas, disciplines in their own right that have come out of chemical engineering. And we're talking about trying to understand chemical processes in an industrial setting. So that also involves reaction kinetics. And what do I mean by understand? We want to optimize an industrial process. We want to control it. So we're talking about mathematical modeling. And if I'm going to use reaction engineering models in my subject, the good news is I don't need to know about the chemical engineering or the physical chemistry, because just as I'm going to give these models to my students, I can take these models out of a reaction engineering book or a physical chemistry book. So I don't need to know chemical engineering or physical chemistry. So I'm talking about this little bit on my Venn diagram here. So what's the simplest possible model? Simplest possible model is when I've got one chemical species A that's going to decompose to give a chemical species B. A long time ago, when I was a chemistry student, I wouldn't have written the differential equation in this way, because I would have just cancelled the V's out. I wouldn't put the V's in there. Well, V is the volume of the reactant. So we can see that the concentration of A is going to decrease exponentially and the concentration of B is going to increase. And at the beginning of the reaction, I won't have any B present in my reactor. It will be equal to 0. And what might is it too simple? Is it too simple to give to students? Well, later on, I'm going to come back to this model and it's going to be a stepping stone to something a bit more interesting. But it's not too simple, is it? If we're teaching the first course on differential equations, we're certainly going to ask students to solve this differential equation. So I could ask students to solve this system, and when I'm teaching science students who haven't done calculus before, I'm pretty certain a large number of them are going to get it wrong, because they're not going to like the fact that I've got a parameter K1 that I've not specified in the equation. They're going to get confused by that. So I'd ask the students to find what's the sum of the concentrations of A plus B, and I'd ask them to reflect upon what do they think it should be based upon what's happening in the chemistry. I'm going to return to that point on the next slide. We could use this very simple model for data fitting. Where are we going to get the data from? Well, you should go and speak to if you have a chemistry faculty, you should go and speak to physical chemists. I'm very confident that there will be chemistry experiments where students do experiments on this kind of system. They will measure the concentrations and they'll have to estimate the value for K1. So you could get data for experiments that your students are actually doing, or you could go to a physical chemistry textbook or a chemical engineering textbook, or you could just make the data up yourself, of course. And you can do two kinds of data fitting for this kind of experiment, because this parameter K1 is going to be a function of temperature. And in this equation here, A1 and E1 are quantities that the chemists are interested in. They've got chemical meaning. And R is the ideal gas constant, so that's a constant. So you could imagine a sequence of experiments when you estimate the value for K1 for a fixed value of temperature, and then you change the temperature and you get a new value for K1, and then you estimate the values for A1 and E1. All right, if we look at this equation with our mathematical glasses on, we can see that if we add the equations together, the right-hand side is going to be 0, and that means there's going to be a conservation relationship. And I'm not expecting first-year science students to realize this. But what I'm expecting first-year science students to realize is, suppose I start with 5 atoms of A, and a little bit later, one of the atoms of A has disappeared, so I've only got 4 atoms of A. Where's that atom of A gone? Well, the chemistry tells me that A goes to B, 1 atom of A goes to 1 atom of B. So if 1 atom of A has disappeared, I've got 1 atom of B. So I've got my 4 atoms of A and my 1 atom of B, so I've got 5 atoms. So the science student should work, well, hopefully the science student should use their knowledge of chemistry to say that the atoms are conserved, and then they should look at the solution that they got for A plus B and see that it's either conserved and it's a success and they did the calculation correctly, or it wasn't a success and they made a mistake. So yes, there's a conservation relationship, and that's implied by the chemistry. All right, the second, maybe it's not the second simplest reaction, but we could extend what we had previously to consider a sequence of reactions. A goes to B, goes to C. And well, I mean, I guess obviously we could ask the students to find the value for C, but it's slightly more interesting if we consider a case where I'm really interested in this intermediate B. That's the product I want to make, and I'm not interested in C at all. And in chemistry, it's quite common that there's more than one reaction occurring, and something that you're interested in is decomposing or taking part in subsequent reactions. So here I can ask the question, suppose I want to maximize the concentration of B, what time do I stop the reaction? So students can solve the differential equations, and then they can differentiate to find dB by dt, and they can put it equal to 0, and they can find the time that's going to stop, and the time that's going to maximize the concentration of B. Now, I want to go on a slight digression now to talk about different kinds of chemical reactors. So a batch reactor is something like, it doesn't necessarily have to be closed, but it's the kind of beaker that you might have used when you did chemistry sometime in the past. And these kind of reactors are good for small scale lab experiments, and they're very good if you don't understand the kinetics of the system and you want to investigate them. But they're not so good for industrial processes, and in industrial processes, we normally want to use a flow reactor. There's 2 kinds of flow reactors. So one flow reactor is I've got some kind of chemical reactor. I'm going to have a reactant stream flowing into the reactor. I'm going to have a product stream leaving the reactor. And inside the reactor, I've got very good agitation. That's going to mean there's no concentration gradients inside the reactor. That means I can use a system of ODEs. And the second kind of reactor is called a plug flow reactor. And now I've got my reactants are flowing in here and my products are leaving here. And I don't have agitation, so I'm going to have a concentration gradient in this direction. And I might even have a concentration gradient in the radial direction as well. So I'm going to model this by using PDEs because I've got spatial gradients. So for this talk, we want to keep things simple. So I'm going to talk about these continuous flow reactors. Oh, it didn't look like that a minute ago, and I checked it on my own computer. All right, what I'm going to do now is I'm going to show you how you go from the batch equation model to the flow equation model. If I was using this for first year students, I wouldn't show them this. I would just give them the model. So these are the equations I had previously, which are for the flow reactors, sorry, for the batch reactor. And what's the difference between a batch reactor and a flow reactor? I've now got this stream of fluid entering the reactor and this stream of fluid leaving the reactor. And so that's what these blue terms are. Q is the flow rate of the stream. And in principle, you might have A, B, and C might be in the feed stream, but usually we're going to assume that B and C are equal to 0 in the flow stream. And now I'm going to divide by the volume. And when I divide by the volume, it introduces the residence time, which is the volume divided by the flow rate. And in engineering, this is the main parameter that we can control. It's easy to control the velocity of the feed stream. So this is my main bifurcation parameter, if you want to use that word. Although there's no bifurcations in a model this simple, but it's the main parameter I can control. So how might I use this model? I mean, I could ask students to solve this model, but I wouldn't do that, because in engineering, we're interested in the steady state behavior. And as mathematicians, we can say it's a linear system of equations. The solution is going to be a sum of exponentials. The eigenvalues are going to be negative. So after some amount of time, I'm going to get very close to the steady state behavior. So one question that you could ask, what's the value for tau that's going to maximize the concentration of B? And there's some industrial applications when it's the concentration of B that you want to maximize. All right, so on this slide, these are the steady state equations, of course, because I've put the derivatives equal to 0. And what is this term B upon tau? Well, the units of this are going to be the concentration of B per second. It's the amount of B that's flowing out of the reactor per unit time. So if I go back here, it's the amount of B per unit time that's leaving the reactor. And a lot of chemical applications, industrial applications, that's the quantity that you want to maximize. You don't want to maximize B. We want to maximize this quantity instead. So we can ask students to find the steady states, calculate B divided by tau, and then maximize the value for P. Has anybody here heard of the Maillard reaction? Now, you don't need to put your hand up and tell me what it is. But you could indicate. No one saying anything. Those of you who've taught classes, all of you will know this is a very typical reaction. You ask a question and there's silence in the class. Well, even you haven't heard of it, but if you like cooking or you like baking, you've used it. And if you like eating, you've been the beneficiary of the Maillard reaction. And there's a lot of, well, chemists can go into a lot of detail as to what the reaction scheme is, but here's a simplification of the reaction scheme. It's 3 consecutive reactions. And you can, I mean, I've almost said this in my second point. You can follow this reaction because there's going to be a color change. So you can follow the color, you can follow the extent of the reaction by measuring the color. And so we do that by measuring the absorbance of the reaction mixture at particular wavelengths. And we can see that what we measure is going to be proportional to the concentration of M. And what's been found is that at small times, the absorbance is proportional to time cubed. And to investigate this, I'm going to use what's called the Paul chemical approximation. Now, the amount of glucose, the amount of sugar is changing. But at very small times, the amount that it's changed by is very small. So I can ignore that and I can put the glucose concentration as a constant and say, well, for small time, it's not changed by a significant amount. So does this simple mathematical model support this conclusion here? So there's the chemistry, and I wouldn't expect the students to write down these set of equations. I'd give them these equations. So these are the equations for this model. And the question for the students is, well, can we solve this system? And then from our solution, can we check, is it true that at small times, the value for M is going to be proportional to T cubed? So can they do a Taylor series expansion of the solution? And you can get parameter values, so you can use parameter values as well and get students to graph things. And for how long is it true that the concentration is proportional to T cubed? And so this particular question, I got the idea for this question from this particular paper, and I came across this paper from a second paper. These links are hopefully clickable, and you can go to the paper if you click on them. This journal doesn't appear to exist anymore, but you can get the paper on ResearchGate. And I've not looked at it for a while, but I have a suspicion that there's a nice little mathematical models that we can get from this paper that we can use in our classes. Because it's certainly nice to use a model when we can say, here's a real chemical process where it's been used. All right. What do I mean by chemical reactor? Now, we might be thinking about the kinds of reactors that we used in chemistry. But a chemical reactor can be something completely different. So here's an example of a problem where a company is discharging a herbicide into a river, and the river's flowing into a marsh, and the marsh is going to be our chemical reactor. And the model for this is this equation here. So it's the equation for a continuously stirred tank reactor. And what I'm going to talk about here, this is a question that I built up from Vogler's book, Elements of Chemical Reaction Engineering. I really like this book because a lot of the questions in this book, they refer back to the chemical engineering research literature. So you can say, here's a model, it actually applies to a real chemical situation. These are the parameter values that have been estimated for the model for this situation. Now analyze the model. So, I mean, we could ask a very basic question, integrate this equation. But I think for this kind of thing, we could do something more interesting. That first of all, we could get students to estimate the value for K1 from batch data. That's actually what I talked about at the very beginning. If I've got a single reaction in the closed reactor, can I estimate the value for K1? Then, I'm not going to be measuring the concentration of A in real time, but I might be measuring it once a day. So if I've got estimates for A as a function of time, can I then estimate what this concentration is that's going into the marsh? And we're not really interested in this quantity. We're interested in this combined quantity here, which has got units of moles per time or kilograms per time, depending upon what you measure A in. This quantity here is going to be, what's the amount of herbicide that's released into the marsh over a specific time? Because if these quantities here are constant, that's just going to be this number times by T. We could set this up as some kind of modeling scenario when the students are representing people from environmental agency. Perhaps they're checking the quality of the water in the marsh. Is the company releasing too much herbicide? Or we could set the modeling scenario as from the perspective of the factory. You go to a conference, you hear a lot of interesting talks, you're very excited. Passage of time, you forget the things that you've learned. By the end of this week, I'll probably have forgotten everything that I've learned. But one thing that I really liked in this conference that I'm not going to forget was this quote from Victoria's talk on the first day. We want students to learn to produce actionable insights. This kind of modeling scenario here, if we set it up from the perspective of, say, the environmental agency, the students are going to be writing a report and making recommendations about what course of action should be taken. So that's something I'm taking away from the conference. We could, generalize the model as well. So at the end, I want to return to the question about breakfast cereals. And this is an industrial mass problem that came up about 30 years ago in New Zealand. And in England and Australia, this is produced by, you can't see the name of the breakfast cereal, but in England, it's called Rice Krispies, and in Australia, it's Rice Bubbles, produced by Kellogg's. And they wanted to understand the cooking process. They've got a grain, what happens during the cooking process. And they had a conceptual model that as the steam penetrates into the brain, the steam's going to lose heat. And this means there's going to be a moving front of steam, and there's going to be a temperature moving front, and they're moving step by step into the brain. And they wanted to know more about this. In food engineering, there's two problems. You've got something that's wet and you want to make it dry, or you've got something that's dry and you want to make it wet. And it's a very complicated process. One reason why it's complicated is the diffusion process is very complicated for steam because the diffusion coefficient is not constant. It's a function of the local concentration of steam. And also your cereal grains are expanding. It might be this size to begin with, but it's this size at the end. That makes the equations more complicated. So this isn't a model that you would give to undergraduate students. But when you're doing these kinds of industrial math problems, you start with the simplest possible model. The simplest possible model is to have a linear diffusion model. And if we're teaching a PDEs course, we certainly teach students how to solve a linear diffusion problem. I wouldn't model the cereal grain as a cylinder, though. I would model it as a sphere. And the industrial company provided the parameter values that we need to know. And the conclusion from this, from using a linear diffusion model, is it only takes 1 minute for heat to penetrate into the center of the grain, but it takes 20 minutes for the steam to penetrate into the center of the grain. So the conclusion for this is that most of your cooking time is that you're waiting for the steam to get inside the grain, and consequently you're overcooking your grain. Now, obviously, you've got to investigate these conclusions using the more complicated models, but there's a simple diffusion model that you could give to students to begin with. So yes, it's a complicated process, but the first step is a linear diffusion model. We teach students how to solve linear diffusion models in spherical coordinates. This is the best paper to read if you want to know more about this problem, because it's the report from the industrial workshop where it was investigated. And even though this is a very obscure Australian publication, you can click on this link here and it will take you to a PDF of the report. So to conclude, reaction engineering gives, I've only talked about very simple models, but there's reaction engineering models that you could use in first year, second year, third year, fourth year subjects. I've talked about linear ODE models, so even models that we could use in our first differential equation subject. Data is available, physical chemistry textbooks, reaction engineering textbooks. Go and speak to your colleagues. They're probably more frightened of you than you are of talking to them. And I've mentioned this breakfast cereal quite often, and I'm not being paid for product placement, and you can't see it anyway. Oh, you can now. I'm not being paid for product placement, but if anyone from Kellogg's is watching this presentation, I'm open to offers. And I'm going to remember from this conference is produce actionable insights. That's something I'm going to do much more in my modeling. And I think I've left time for one short question.
That was fun.
Yes, I think it is fun. And it's fun to ask students to look at breakfast cereals. I should say in New Zealand, this did come out in the press. And people in New Zealand were very interested in the idea that mathematics might improve their breakfast experience. And for a few years after this, Mark kept getting letters from New Zealand citizens. Is it really true that we can use mathematics to improve breakfast cereals?
I have a question.
Yes.
I mean, do you handle non-linearities for these students? I mean, or you said you use linear models, but the non-linearity will lead to some interesting issues.
That's exactly, yeah. That's exactly right. That when you look at more complicated chemical mechanisms, there's going to be interesting bifurcations. And particularly if the reactions are producing heat, there's a classic problem in chemical engineering, which is when you have a first order reaction, but it releases heat and it's occurring in a reactor. And those kinds of problems aren't appropriate for a very first subject in differential equations, because I'm not teaching students about bifurcations in those subjects. But when I teach higher level subjects, then I do use those models in higher level subjects. And today I just wanted to talk about more simple models when there were no bifurcations.
Thank you.
Maybe next year I'll talk about models which have got bifurcations.
Yeah.
May I ask if you ask students to read any of the papers you mentioned, or you provide them the information?
It
Do
would
you
depend upon
adopt papers for your students?
It would depend upon what level subject I was teaching and what background the students had. So in a first year subject, when students are just learning differential equations for the first time, if they were chemistry students, I might ask them to go and read a chemistry paper, but I wouldn't ask math students to do that. Whereas in a later level subject for fourth year students, I would be more confident in saying to the math students, well, you need to go away and read this chemistry paper, because after all, that's what we have to do in modeling, don't we? Quite often, we have to read papers outside of our expertise to gain some insights into what it is that we're modeling. So yes, it depends upon the background of the students and the level of the subject.
Thank you.
Thank you so much, Mark, for the presentation. It was really great.